Alright, in this video, we show that the linear transformation of a Gaussian random vector is also a Gaussian random vector. More specifically, if x is a random vector that follows a normal distribution with the mean of mu x and the variance covariance of sigma x, and if we transform this vector x by the linear transformation defined by this matrix phi to define a new random vector y, then this random vector y follows another normal distribution with the mean of phi transpose mu x and the variance covariance of phi transpose sigma x phi. Okay, let's start. First, let's review the probability density function for the normal distribution. So suppose B is some bounded region in the n-dimensional space, then the probability that the random vector resides in this region is given by this integral. 1 over square root of 2 pi to the power of n, and the determinant of sigma x times exponential of x minus mu x transpose sigma x inverse times x minus mu x over 2 and dx. Now, let's calculate the mean and the covariance of the new random vector y. So random vector y is defined by this linear transformation, and let's use that. So the mean of y is the expectation value of y, and the distribution is, of course, the distribution of y, right? And this is equal to, so since we are using linear transformation, we have this. So expectation value of phi transpose times x. And now we calculate this expectation by using the density of x. But since this is a linear transformation and the operation of taking expectation value is a linear operation, so we can take this phi outside the expectation. And therefore, and this is by the given condition, it's mu x. So this phi transpose times mu x is the expectation value of y. And next, let's calculate the covariance of y. So sigma y is the expectation value of y minus mu y and y minus mu y transpose. Okay, now express this in terms of x. We have phi transpose of x minus phi transpose of mu x times phi transpose of x minus phi transpose of mu x transpose. So here we rearrange this transpose part to have the following. So first we take this out, factorize, and we have x minus mu x here. And if we distribute this transposition operation, then we have x minus mu x transpose times phi. Again, this operation of taking expectation value is a linear operation, so we can take these phi transpose and phi out. But of course, these are matrix operations, so we can't change the order of multiplication. So we just preserve it to have x minus mu x, x minus mu x transpose, and phi outside. Okay, but this part is just sigma x. So in the end, we have phi transpose, sigma x, and phi. So these are the mean and covariance of the new random variable y. Now let's calculate the probability that y resides in some bounded region in the n-dimensional space. So by definition of y, this probability is equal to phi transpose x is in B. But since we are assuming that this matrix phi is invertible, this linear transformation is bijection. So this is equal to P x in the transpose inverse of B. And this probability is given by this phi transpose inverse B and 1 over square root of 2 pi to the power of n and the determinant of sigma x exponential and x minus mu x transpose and sigma x inverse x minus mu x over 2 dx. Now let's change the variables in this integral from x to y by this transformation. X is equal to phi transpose inverse of y. So that means we have the Jacobian of the determinant of this, right? So dx is the determinant of phi transpose inverse of n dy, which is actually 1 over the determinant of phi. So by this change of variable, this integral becomes, so integral over the region B, and let's put this as it is here, sigma x determinant and exponential. So we change this x to this and mu x to phi transpose inverse times mu x. So that if we factorize this, we have y minus mu y transpose and phi inverse and sigma x inverse, and for this one we have phi transpose inverse and y minus mu y over 2, and don't forget the Jacobian, times 1 over this dy. Now let's consider this part. So this one, phi inverse times sigma x inverse times phi transpose inverse is the inverse of this. Phi transpose sigma x phi, so everything inverse. But remember, this is sigma y, so the covariance of the random vector y, so it's this. And also, let's put this one inside this square root, so it becomes squared inside the root. Okay, so now the integral becomes 1 over square root of 2 pi to the power of n sigma x determinant times phi determinant squared. And we have exponential negative y minus mu y transpose sigma y inverse y minus mu y over 2 dy. And now consider this part. And the determinant of phi is equal to the determinant of phi transpose. So let's put this square into the product of determinant of phi times determinant of phi transpose. So this part is equal to sigma x transpose determinant and phi transpose times phi, all determinants. So this is equal to, so since determinants are just real numbers, we can swap the orders, and this is equal to phi transpose sigma x and phi. And the product of determinant is the determinant of the product. So this is equal to the determinant of phi transpose sigma x and phi, which is the determinant of sigma y. So we can replace this part by the determinant of sigma y. So that means the probability density of y is this, which is the density function of the normal distribution with the mean of mu y and the variance covariance matrix of sigma y. And we are done. Okay, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.